That's what I need to do. And put that. Okay. Hey. Okay, hello, everybody. Sorry for the late start here. Apologies about that. Yes, we'll get a little bit late start, but I think we'll be in good shape for finishing up what we need to do here today. Thank you very much for everybody for coming on out here today. I really appreciate it. How's everybody doing tonight? Hopefully everybody is doing fantastic tonight. I'll give you guys a few minutes, and we'll get started, but we can get through stuff with no issue whatsoever. Apologies for the late start here. Apologies for the late start here, but I'm glad all of you could come out here today and have a fantastic day. Hopefully, you've had a fantastic night, a fantastic evening. How we doing? Good evening. Good early evening indeed, Focus. Good early evening indeed. I hope you're doing well, Focus. Hopefully you're doing really, really well. Hello, make me proud. How we doing? How we doing this fine evening? How's everybody doing this fine evening? Again, apologies for the late start here. Apologies for the late start, but we will certainly get everything done here regardless of that. We're gonna say, Bill, good evening. Hey, I got a question for you, Bill. Were you able to log in again afterwards? Everything cool with my math lab? Let me just ask you that. Hopefully everything is pretty copacetic with my math lab now. Excelente. Okay, that's good. That's good to hear, Bill. All right, that is wonderful to hear. I'm glad that got squared away. I'm glad we got that thing going. All right. Good beans, man. Good beans. All right. Very, very happy to hear that. Very happy to hear that. All right. Glad we were able to fix your problem, man. I know it took a while, but you know what? Perseverance pays off. Perseverance pays off, and we were able to get stuff done. Everybody got plans for the very nice long weekend? It's Labor Day on Monday, so you guys got a longer weekend, maybe a 3-day weekend, 4-day weekend if you don't work on Fridays, or if you're off on Fridays, I don't know. But 3-4-day weekend. Everybody got plans? Going out for barbecue? Going out having fun? Pool party at your aunt and uncle's on Sunday. Heck yeah! Whoop! I can respect that, man. I can totally respect that. That's legit. Now that sounds like a lot of fun with a little bit of barbecue on the side, have a little bit of pool party, enjoy some hamburgers, some hot dogs, a little bit of swimming, spend time with the fam. There you go. That's what I'm talking about, man. That's what I'm talking about. Alrighty. Okay, we're going to get started in just a second here. We'll get hopefully a few more people start trickling in, and then we'll go ahead and start here in just a little bit less than a minute. Alrighty. We'll give about 20 more seconds here, then we'll get going. All right, let's get going here. All right, so let's do some intros. Let's get going, and we'll get started here. There we go. Better. Okay, let's get started today. Welcome back to Thursday, end of the week time today. So today, everybody, we're going to pick up where we left off last time on Tuesday. Last time on Tuesday, we went ahead and we actually looked at a data set. We arranged it in terms of a frequency distribution and a relative frequency distribution. Now, one of the things that I said here at the end of class last time is I saved the example here on my computer, and then we're going to be reusing this example here for looking at some other things, other questions that we'll be talking about here for today. So that's essentially what we're going to be doing here. We're going to be revisiting that same example from last time, and we're going to be taking some of that data and arranging it in a different way, again, organizing in a different way to see if we can draw some conclusions based on what we see. So let's go ahead and take a look here at our previous example, just as a good sign out. So let's go to the big board. All right, so taking a look at the big board, this is what we had here previously, okay? So as you can see here on the screen, we have the data set here off to the left. All right, we have the scores, the categories that we talked about here last time, the frequency and the relative frequency here for each individual category at the end of the day. Okay, now, taking a look at this here very carefully, again, what we're going to want to be using here is we're going to actually use both of these here today. We're going to be looking at the frequency distribution, and we'll also look at the data set here. We're going to see just a couple of different ways to arrange this data in a slightly different light. But before we do that, we got a couple questions, pardon me, to go ahead and answer. Let's go back to our handout here. Now, going back to our handout here, let's maybe make this a bit bigger here so read. Okay. So we went up to question number 3 last time, where we actually constructed that relative frequency distribution. That's what, again, just as a reminder here, that was this part right here with the relative frequency. This was question number 3. Today, we're going to start at question number 4 here on the handout, and then we'll go ahead and work our way forward. All right, so let's look at number 4. All right, and then we'll start number 4, and we'll work our way up. All right, so number 4, what type of graphs can we make using frequency and relative frequency? Okay, so what type of graphs can we make here? Well, fairly simple. Relative frequency and frequency charts and relative frequency charts, we can make, say, bar charts from them. We can make, regular pie charts, pie graphs from those. We can make line charts from those, okay, line charts, or we can even make Pareto charts. Now, Pareto charts, as I listed here, is a descending bar chart. So essentially, start at the biggest bar, then the next biggest, then the next bar here, which is slightly smaller, and then the next bar, which is slightly smaller. So you get the smallest bar at the very end, and then that's going to be a Pareto chart. So biggest, next biggest, all the way to the smallest. Okay, so what we're going to be looking at here, we're going to be looking at how we can construct one of these types of charts here using the example from the data set that we had just talked about here last time. Now, in order for us to understand that, though, we do need to build a little bit of a basis, a foundation from that particular point. Let's go ahead and take a look here at number 5. All right. So number 5 says, what is a lower class limit, upper class limit, and class width? Now, one of the things that I talked about here is we talked about here in our previous example, and I'll go ahead and put this as a 50. We'll put this as a half screen on here. Is that from here, we had categories like within the 50s. So we said scores between 50 and 59, 60 to 69, 70 to 79, 80 to 89, and 90 to 99. So each one of these categories that we've discussed here are essentially a class. This is just another way to say category or group. Now I'm going to use the term class here because, again, some formal terms here will also use the word class. So it's important to at least kind of get to know what it means in that particular context. Why is this important? Well, let's take a look here at these first two definitions. First, we have a lower class limit. A lower class limit is the lowest value in a class. All right, so that would mean that if we looked at 50 to 59, then the lowest value in that class is the score of 50. If we looked at 60 to 69, the lowest value in that class or category, however you want to call it, is going to be 60. 70 to 79, the lowest value, the lower class limit in that category or class is going to be 70, and so on and so forth. On the flip side here, we have the upper class limit, which is the highest value in a class. So again, that's just basically the very largest value that we have here. So again, 50 to 59, the upper class limit would be 59, the highest score in that class. Again, it'd be 60 to 69. Okay, so the highest value in that class would be 69. Okay, that's the biggest value there. And then the class width, there you go, easy peasy, squeezy. All right, Class width here, lower class limit of class 2 minus the lower class limit of class 1. All right, that's how we're going to define the class width. So the class width here is, again, what's the difference between the lower class limit of class 2 and the lower class limit of class 1? Let's talk about that here for just a moment. What do I claim to be class 1 and class 2? What exactly does that mean in this context? In this context, that means it says, okay, class number 1 here would be, say, the scores in the 50s, but class number 2 here is the next subsequent class right after that. So the next consecutive class would be class number 2. So I'm not skipping like categories or classes. I'm saying what would be logically the next category or class. Well, that's going to be class number 2. And I take the lower class limits of each in order to determine how many scores would be in each category or whatever the case may be. In this case here, I take 60 minus 50, so that's where I get 10 as my class width. Now, the reason why we do this here specifically is because people get the common misconception that class width in this particular example, for example here, would be 9. All right, you would say, okay, well, the class width is 59 minus 50, but people often forget, be like, well, how many scores are actually in that particular category? Well, there's 50, 51, 52, 53, 54, 55, 56, 57, 58, and 59. There are 10 values in that class. Not 9 values, but 10 values, okay? So important to know here that we actually have 10 values in that class, not 9. That's why we take the lower class limit of the next one up as opposed to the highest class minus the lowest. So that's why we actually look at class width that way instead of the other way. So again, hence why it's listed there like so. Okay. Any questions about that so far? All right. Good stuff. Okay. Let's take a good look here at number 6. All right. No? Okay. Just making sure here. Let's take a good look here at number 6. All right. So number 6 says, how do we construct a frequency distribution with the proper number of classes? We do have to be very specific on how we construct these proper number of classes here. Again, there are particular guidelines to follow here if we're going to construct these charts and construct these frequency distributions. First thing is that the class width must be consistent for every class. So if you remember how we did this example here last time, the way we did this example is I picked scores from 50 to 59 as my first class, as my first category. Now, since that specifically had a class width of 10, that means that the next category or the next class also needs to be a class width of 10. That's why we can't be skipping here. We can't skip scores, we can't skip around. We're not allowed to do anything like that. So I can't just magically say, well, I have 50 to 59 and I'm going to skip over to the 70s. Even if you don't have, so let's say for example here, this is a quick example. Let's say there were no scores in the 60s, okay? Let's say there were 0 scores in the 60s. No student got a 60 in our data set. Even if there are no scores in the 60s, I still need to represent 60 to 69. I'm not allowed to skip a category even if there's actually a frequency of 0. All right, so that's something to keep in mind. Even with the frequency of 0, I still need to represent it at the end of the day. So no skipsies, all right? That's how it works. All right, so, and every single class must have the same class width at the end of the day. So I can't say 50 to 59 and then 60 to 64. I'm not allowed to do that either. Okay, that's not the same. All right, that's not the same. All right, so as I put here, you cannot skip scores even if the frequency is 0. And then also we talk about the maximum number of classes here. Again, our goal here in talking about how to do these particular problems is basically to consolidate everything down into a easy to read table. That's essentially what we're doing here. Because instead of 16 scores like in our example, let's say we had thousands of scores. Well then, you know what? Maybe it's a lot easier just try and consolidate it down into those things, into a limited amount of categories or classes than just, hundreds of them. So the max number of classes that you want is between 10 to 15. Okay, so 10 to 15 classes is typically the maximum number of classes that you want here at the end of the day. Okay, so that's perfectly fine. Okay. Finally, the last thing that I want to point out here is we do not want to make every single data item a class. That is not what we're setting out to do. So even if each data item occurs once, then you're going to say, oh, the 71 gets 1. And then basically you say, well, 72 is 0 because there's no 72s. No. We do not make every single data item a class. That is not how it works when we are arranging data, because you want a maximum of 10 to 15 classes, okay? So only 10 to 15 categories. So you do not make every single one a 1 or a 0 just because you think it's easier. That's too long and too unwieldy, especially when you're dealing with thousands or hundreds of data items. All right. So let's take a good look here at number 7. All right, now let's take a look here at number 7 is what is a histogram and some properties. So we're going to arrange this in this case here. What we're going to specifically look at here is what you see here on the screen, which is the frequency distribution. So what's a histogram? A histogram is a connected bar chart that represents the frequency or relative frequency distribution. Okay, so again, specifically, this is a connected bar chart, not a separate bar chart, but a connected bar chart. All right. So let's take a good look here on how we can go ahead and construct this together in this particular instance. So we're going to look at the frequency distribution here. What we want to do is make a histogram here based on this frequency distribution. Now, in order for us to do so, go ahead and take a look. All right, so we're going to have two axes that kind of look like this. All right, so on the left here, we're going to have a frequency. And here we have scores. Okay. So we're going to put in each category down here, put a little tick mark. So tick mark here for 50 to 59. 60 to 69. 70 to 79. And we'll have 80 to 89. And then I'll pick a little here for 90 to 99. Okay, so here are each one of our categories. We also have some frequencies we'll need to fill in, so we'll fill those in. So we'll have 1, and 2, and 3, and a 4, and a 5. Okay, so since we have a max frequency of 5, then let's go up to 5. Okay, so let's talk about how we can construct these and put these together. And honestly, they're not too hard. Just have to look at it carefully. So the first thing that we have to remind ourselves here is that we're going to start, the very first bar that we draw here is incredibly important. So for example here, let's take a look at 50 to 59. 50 to 59 here had a frequency of 2. Now, since 50 to 59 here had a frequency of 2, we want to draw our bar here up to 2. But where are we going to start? Well, if you see here on the 50 to 59 here, we're going to start a little bit to the left of that tick mark here for 50 to 59. All right, and we're not going to start directly from the left, okay? So understand that. We're not starting directly from the left. We're starting a little bit to the left of that 50 to 59. And then we're going to go up. And then we're going to stop at 2, and then cut to the right, and then come down in between go to the right of that 50 to 59 tick mark, and then, stop and draw the bar here between the 50 to 59 and 60 to 69, just like so. Again, the reason why I'm not starting at all the way to the left here is because 0 is not represented in my particular data set. If 0 is represented in the data set, it's perfectly fine to start all the way to the left. So I put a little note here in regards to that. I'll come back to this in a second. Oh, that's the wrong note. Here is that we do not start the histogram directly from the left unless we have 0 as part of the category or class. Okay, so that is something to keep in note. If we do have 0 as part of the category or class, start directly from the left and make a bar, fine. But if you don't, well, no. One other thing to keep in mind is in part of the histogram is that this tick mark here should be in the middle of the bar, middle of each bar that we're going to draw out. Okay, so it's not going to be on the left, it's not going to be on the right, it's going to be that tick mark here will be smack dab in the middle of each of the bars that we're going to draw out. No, this is not the best representation of middle, but you get what I'm saying. Okay, so the next one here is 3. Now 60 to 69 here is 3. Go up to 3. And then we'll go a little bit to the right of that 60 to 69, and we'll bring it down, just like so. Okay. All right, so that's 60 to 69. Good stuff. Next, we're going to have 70 to 79. All right, so that's going to be a frequency of 5. We'll start from the upper right here. We'll go up to 5. And we're going to cut across here, that tick mark, and right between the 70 and 80 tick mark, we'll bring that bar down just like so. All right. Next, we'll look at the 80 to 89, which is 4. So we're going to look at the bar here, see where 4 is. 4 is right here. I'm going to start here. Again, each bar has to be connected. There we go. You got it, just like so. Easy peasy lemon squeezy. And then 90 to 99 is 2. So we'll see where 2 is. 2 is right about here-ish. So again, go here. Cut to the right of that tick mark there for 90 to 99. And there we go. We have our last bar like so. Okay. Any questions about that? That is our histogram. Again, essentially that's what our distribution is looking like here. What our frequency distribution looks like here in a nutshell, pictorially. Any questions about a histogram? Nope. All right. Okay, good. Let's take a good look here then. Let's look at the next question then. Shouldn't be too hard. Oh. All right. That was pretty simple. All right. Next question here. Let's talk about stem and leaf plots. So the next thing we'll talk about here is how do we arrange our data items in the data set. So another way to look at the data items in the data set is specifically looking at each individual data item and putting them, say, in a nice little chart or in order if you want to look at it from that perspective. So the way we do that here is using a stem and leaf plot. So what are stem and leaf plots and some things to remember? So in this case, a stem and leaf plot here is basically going to represent every data item in the data set. All right. And again, as I put in a note here, every stem must be represented even if there are no leaves. So just like we talked about here, even if there are no scores in the 60s, I'm still going to have a stem of 6, which will represent the 60s, even if I don't have any leaves. And again, leaves can repeat here. So the easiest way to think about it is that the stem here would be the tens digit and the leaves here would be the ones digit. Well, you're probably saying that's a lot of abstraction that you're really saying, but you're not actually showing me what the heck that means. I would contend to you, you're right. All right. So I need to actually zoom out of this. Just a moment. Okay. And let's make a stem and leaf plot here. Again, we're going to use this data set here that we have in the upper left-hand corner here. So I'm going to have two columns here. I'm going to have a stem. Sorry. Let me use a different color here. Use blue. We have a stem, and we got leaves. Okay, so we have stem and we got leaves. That's fine, no problem. All right. So for the stem here, what we're going to do is, since we have scores in the 50s, 60s, 70s, 80s, and 90s, so we're going to have 5. 5 will represent, in the stem, will represent 50s. 6 for 60s, 7 for 70s, 8 for 80s, and finally 9 for 90s. All right. That looks pretty terrible, I know. All right. Okay, let's look at 5. Let's look at 5, 6, 7, 8, 9, again, 50, 60, 70, 80, 90s. Let's look at our data set here, okay? So take a look at this very first data item. It's the number 73, okay? So 73 is our first data item in the data set. So if we have 73 here, 7 is going to be our stem, and 3 here is going to be our leaf. So let's see if I can find it here, sorry. So we have 70 and a 3. So 7, 3, 73. Okay? That's how we're going to read this off of a stem and leaf plot. Let's look at the next one here. It is 62. All right, 6 is the stem for 60, and the leaf here will be 2. So 62. All right? Hopefully that makes a lot of sense. I hope so anyway. But let's look at each one here. All right. So let me ask you guys here, what leaves are we going to have for the scores in the 50s? What leaves will we have here for the scores in the 50s? Can anybody tell me here, what leaves are we going to have for scores in the 50s? Okay. Good. 1 and 4, 4 and 1. Either way, it doesn't matter. I agree with both. They both mean the same thing to me. So we're going to have 1 for 51, and then another one for 54. Now, just to let you know, for these examples here, you don't have to put in numerical order if you don't want to. We will be putting in numerical order when we talk about mean, median, and mode if we have a stem and leaf plot here. But for the purpose of these examples, you could have 4 and 1 or 1 and 4. I won't care either way because, again, we just want to be able to learn the concept here. So putting in order is not required here for this example, or we're at this stage, I guess I should say. Okay, very good. That is correct. All right. Let's zoom in a bit, and we'll go on to 6s here. What about the 60s? What scores are in the 60s that we can make as part of our stem and leaf plot here? What numbers are going to be in our stem and leaf plot here? 2 and 7. 2, 3, 7. Okay, so we have 3 scores. We have 2. We have 2 already represented. And we have 7 and 3. Good. Perfect. Plus 3. Plus 3. There you go. Nice. All right, so 2, 7, and 3 is correct. Now, just to let you know, by the way, I'm going to give you a friendly reminder here, as we're going to work on the 70s, of course. As a friendly reminder about stem and leaf plots here, I put the second note here. Leaves can repeat, so just don't forget about that. You can have the same number twice as leaves, again, because each one of those represents an individual data item within the data set. So we want each individual data item to be represented at the end of the day. So don't worry if numbers repeat. That's fine. There just means they're two separate data items. It means the two different students got the same score, but you don't bundle them into one. Take them both as is. All right, how about the 70s? What scores are in the 70s here? What are we going to have for 70s? About the 70s here. What are our leaves for 70? Now, don't forget here, by the way, we have 5 scores in the 70s. That's what the frequency said. So if I have 5 scores in the 70s, I should have 5 leaves. All right? So be careful there, make me proud. It's not just 2 of them, right? I need to reflect 5 scores in the 70s. That's how it has to be. That's okay. I'm here to help, my man. If I take off my glasses, I'm the same as you. Let's see here. Strolling, I think you have 1 too many because you have 6 numbers. Excuse me, my lady. I usually say that for everybody, to be fair, but I do not want to misgender you. That'd be bad too. Strolling, I think you have 1 too many because you have 6 values in your list. I think you wrote 3 2 times. We have 3 for 73. We have 71, so 1. So 3, 1, 8, 0, and 4. All right. So 3, 1, 8, 0, and 4. Actually, to be fair, I don't know what anybody's genders are when they come into my chat. You guys are like, okay, you're all chill dudes to me. Everybody's a chill dude. Dude or dudette. All right. Okay. Yeah, so one thing to keep in mind here, Strolling, is that once you make your frequency distribution, if you're putting it in a stem and leaf plot here, right, just make sure you match it to your frequency, right? Because you should have, say, if I have a frequency of 2 in 50 to 59, I should have 2 leaves. Like 2 numbers in that category, 2 leaves. 5 numbers in that category for the 70s, I should have 5 leaves. What about the 80s? Let's look at the 80s. What are my leaves for the 80s? What are my leaves for the 80s? Eight 8089. Okay, so 8089 is correct. Good. So we had that 80. Yeah, there you go. There you go. Sounds like the last one should have been a 9. Okay, fine. All right, 8089. All right, perfect. All right, excellent. Again, as we can see here, that's a fair question. Make me proud. In this case here, make me proud. Order will not matter because again, we're just talking about the concept, kind of introducing the concept of stem and leaf plot. So for these examples in this section, the order really doesn't matter whatsoever. But in the future section in chapter 3, we are going to order this stem and leaf plot, or if we do use a stem and leaf plot, we are going to put this in order. We are going to put it in order, like numerical order. So if you wanted to do it, it'd be like For example, you put like 0, 8, 8, 9, as an example if you wanted to put it in order. But for these examples in this section, we're just trying to put it together like that. Is this plot also doable for hundreds of thousands? Yes, absolutely, absolutely. It is. I will show that off here in just a second. Let's do the 90s, and I'll show you how it would work here with hundreds here. Focus at the hydrate. You got it, my man. All right. All right. All right. What about the 90s here? Sorry, let me scroll up here because I don't have the scores here. All right. So let's look at the scores for the 90s here. We have 2 of them. So that should be what? 7 and 9. Okay, that is correct. 7 and 9. That's correct. The strolling was right on top of that. 7 and 9. Perfect. All right. Okay, so this is our stem and leaf plot here for our frequency with again with our data set. Excuse me, for all the data items reflecting all the data items within the data set. Now, to answer your question there, Horitz, about is this doable with hundreds of thousands? The answer is yes. You with the stem and leaf plot, you're not limited to just single numbers. Like, although we put this, 9 represents 90 or 8 represents 80. If you wanted to put 100, like let's say, you're talking about scores like 105% or whatever, you could put 10 here. That's fine. You could put a double-digit number here as a stem, and this would represent 100. 100 and what? You could say 105. Okay, so this would be 105, 105. Okay, you can do this even for thousands. So you could put the number 100 here, and this would be 1003. Okay, now the reason why you would do this specifically is because, again, why would you set the stems this way is because you set the classes here beforehand by tens, right? You went 50s, 60s, 70s, 80s, 90s. So because of the way you designated the classes, you're like, okay, I'm going to go in this order here. This is going to be, I'm going to go by tens, so I'm going to put my stem as the first few digits, and then the last number here is going to be the leaves, okay? Now you could set this up different ways, but the easiest way is to probably do it in this manner if you need to absolutely do so. So, yeah. So is this plot doable for hundreds and thousands? There you go. That's the way to kind of directly do it if you absolutely need to do it that way. So, cool. Yeah, great question. Great question. All right. Any other questions before we move forward? Any other questions? All right. Cool. All right. Very good. Okay. Oops, I meant to go back to the handout. My B. All right. Let's go ahead and move forward here. All right. I'm going to go back to the paint tool here in just a second. But next thing is going to talk about number 9. All right, so let's talk about number 9 here. Now that we have a stem and leaf plot, we've been able to put these two together. Let's talk about some shapes of distributions. We saw in the histogram here, actually, let's go back to our example here. We saw in the histogram here what the shape of this particular frequency distribution is underneath this particular example. But there are some generic shapes of distributions that we can certainly talk about, and they certainly do have their own implications. Now we're just going to go ahead and identify them. And one of them in particular we'll talk about a little bit, but and the others here are pretty much your standard fare sort of things that don't require too much. But let's talk about the types of distributions that you see. So we can look at it from a histogram point of view, which is what we're going to use. So let's say the histogram looked like this. Okay, so let's say it looks something akin to this. All right. So this particular type of distribution, this is a uniform distribution. All right, so this is a uniform distribution. That means, again, everything is the same across the board. So if I had in my if I had my frequency distribution, like 4 students got 50s, 4 students got 60s, 4 students got 70s, and so on, everything was a 4. Okay, that's a uniform distribution. So everything's perfectly flat, the same every single category. Fine. Pretty boring, pretty standard. It's like, it's there. All right, let's talk about the next one here. Okay, so this particular distribution is what we call a skewed right distribution. This is not dependent on where the highest bar is in the graph. This is actually more dependent on why they call it skewed right is because the tail of the distribution is going to the right. Okay, so the tail of the distribution is going to the right, hence why we call it skewed right. Okay, so that is a skewed right distribution here in that instance. All right. All right. On the flip side here, all right, so would be just the opposite here. This would be a skewed left distribution. Okay, so this would be a skewed left distribution. All right. So skewed left, that's essentially what you have here. No problem. Easy peasy. All right. So just the opposite. Again, the tail is going off to the left. Again, not depend on the biggest bar, just where the tail is going. All right. Finally, and probably the most important type of distribution here that we are going to talk about here in greater detail in other chapters in this textbook is this last type of distribution. Let's talk about this one here. Okay, this distribution here is what we call a normal distribution. Okay, or again, probably you've heard of the term maybe bell-shaped kind of distribution, bell-shaped curve. A bell-shaped kind of distribution. In any case, however you want to call it here, this is the most ideal distribution that we want to be in, right? This is, again, one of those types of distributions we are going to explore here, especially when we talk about probability. If we talk about probability, a normal distribution is the ideal of most ideals that you want to fall underneath any given scenario because it provides the most balanced scenario here. Again, it's like symmetrical, does the whole 9 yards. We'll talk about it in more detail once we get to that point. But you'll see this pop up quite a bit here once we get to like chapter 5 and whatnot, talking about normal types of distributions and how this is where we want to be when we want to talk about getting the most unbiased data as possible, I suppose is the best way to put it. Like for example here, like I like using this example a lot. So like teachers back in the 70s and 80s thought if you're making the Ferris test that it should follow a normal distribution, should follow a bell-shaped curve, meaning to say, let's say a few people got A's, a few more people got B's, the majority of students got C's, the same amount of people who, you have people who, number of people who got D's is the same amount of people who got B's, and the number of people who got F's is the same amount of people who got A's. So that would be representative of a normal distribution of some type. And like I said, we'll explore a lot more of this, not in the next chapter in a capacity and also in chapter 5 as well. We'll be seeing some properties and understanding how this works and why it's so important in the realm of statistics. Okay. All right. Any questions about those before I move forward? Got just a couple more questions to go, but any questions about that before we move forward? Okay. Let's go ahead and move forward then. Okay. Next, let's look at number 10. Now, number 10 here is going to be the last question here of section 2.2, which is basically talking about what is a time series plot. A time series plot is a line graph that represents a stretch or period of time. So the best example of a time series plot is going to be a stock chart. A stock chart probably is one of the best and easiest ways to basically understand what a time series plot looks like. So let's take a good look here at a stock chart. Let's go to my favorite friend, Apple stock. Okay, so here's Apple stock for the day. Okay, it was up some amount of money, down some amount of money. Again, I don't really care what it's up or down like. What I do care about it is I can take a look at it, the progress of the stock price for the day, or I can take a look at the progress of the stock price for the past 5 days, or the past month, or the past 6 months. Again, this would be, again, a time series plot. So the past 6 months, it went from 122 up to 153, what it was today. Again, looking at year to date, or looking at, say, the past 1 year, beginning of the year, or again, from last year, past 5 years, or again, since its inception, it doesn't really matter. It is what it is. Okay. But you get the general gist on about how things work. It's just that easy how to look at a time series plot. All right, not too hard, and that's effectively the end of that particular section. All right. Now, the last thing that we'll need to talk about here, talk about the last thing. All right, so the last thing we're going to talk about here is talking about section 2.3, the last section here, chapter 2, which is talking about how can graphs be misleading? How can graphs be misleading? So, how can graphs be misleading here? So the way graphs can be misleading is that you have to be careful about the scaling or proportions or sources. It's just as important here. But you know what? Just describing how graphs can be misleading is certainly one thing. Showing you how graphs can be misleading is certainly a lot more valuable. Actually, let me bring this up here. Okay. I'm going to show you a very famous image that was actually shown on television a very long time ago. But I want you to take a look at this little chart here. Okay, let's take a look at this chart. Can anybody tell me here, what is wrong with this pie chart? This was made during the 2012 presidential election run, but for the GOP candidates. But what is wrong with this pie chart? What's wrong with it? Anybody tell me, what is wrong? What do you see that's wrong here? You guys tell me, what's wrong with this pie chart here? They don't add up. Yeah, right? Certainly don't add up to 100, right? That's way more than 100%. I totally agree. All right, totally fair. So that's one way that it's misleading. All right. What else? Total's too high, right? 100% true, even though it's not 100%. Way more than that. What else is wrong? So it doesn't add up to 100%. There's what else? What else is wrong with this chart here? What else do you think is wrong with this chart? Again, you just got to be careful about certain things here. The size is not proportionate to the value of m. That is correct, Strolling. Absolutely right, right? So 70% looks like 63% looks like 60%. They all look they all look pretty similar, so their proportions are pretty bad. Division of, yeah, exactly. Division of colors don't match what they represent. 100% right, Bill. That's correct. All right. There is a third problem here. So we have first two problems, again, greater than 100% true. Proportions are totally wrong. Absolutely true. There's a third problem here. It's more of a subtle problem, but look carefully. What else is a problem with this pie chart here? What else is a problem with this pie chart? One more thing that's wrong with this pie chart here. What do you guys think? Subtle one, but it's there. Yeah, that's right. That's right, Horitz. The horse source is just opinions. Like, that's just the... No, that's true. You're right. The source is just opinions. You're like, it's just opinions. Like, I don't understand what this source is. Like, the source doesn't make any sense at all. It's like, whose opinion's dynamic or something? Like, I don't know who that is. Or how the methodology was. Like, I have no idea. So can I trust a graph like this? The answer is not really. Not at all, really. This is like the biggest fail of graphs ever. But again, it's certainly something to keep in mind when you talk about things like this. You know, one of the most famous graphs ever. Now, again, one of the things to keep in mind here, and one thing that I do want to point out here, is that these graphs here that are made to basically push certain kind of narratives. In this case, whether it be a political narrative, like you should support these GOP candidates or Republican candidates because of blah, blah, blah. Now, let me be honest about this channel here. This channel is not a political channel, right? I don't talk about politics in this class. What I am talking about here is how you can use statistics to push a narrative in one direction or the other. All right. Now, to be fair here, it works on both sides of the aisle. Okay. It doesn't mean that it's just Fox News that basically tells you you have these bad graphs. No, both sides of the aisle, whether it be Fox or whether the MSNBC, which is a Democratic-leaning, channel, they both do this same thing in order to push a particular political narrative in order to get people to believe, whatever they want to believe using the statistics they have. Again, statistics lie. They can lie if you manipulate the numbers enough. So the thing is, a lot of times you kind of have to read between the lines in order to understand what, to really realize, hey, what the reality is behind the situation. Let me show you another situation here really quick. This one's an old Fox chart here. Now, this one's really careful. You got to be really careful about this one here. Tell me what is wrong with this line chart. What's wrong with this line chart here? What is wrong with this line chart? There is one thing wrong in this line chart. And if you look carefully, you can figure it out. What do you think? What is wrong with this line chart here? I'll give you a hint. The hint is look at the numbers very carefully. Look at the numbers on the line chart very carefully. What numbers in particular? Yeah, the numbers are fine. But what about the numbers in particular which number in particular seems very wrong here? There's one number out of all of them that is very wrong. 8 and 9 are fine. Again, you have to look carefully here. Ah, there you go, Stella. 8.6. Look at the very last number off to the right. Do you see the 8.6% here? The 8.6% here is at the same level as 9%. So if you're trying to push a particular political narrative telling me Obama sucks, be like, this is the unemployment rate underneath Obama. Well, 8.6% is not the same as 9. It would mean that it actually decreased over that period of time. But you're pushing a narrative that it's actually exactly the same, which is incorrect. So, that's something that you have to keep in mind. Let me show you the other half of the aisle here. This is like, Republican kind of charts. But of course, I have to look at both sides carefully. You know, let's not lie here. Both of these are pretty bad, and I want to showcase both sides of the aisle because at the same time, I just want to say, hey, it's not limited to one side because that's not fair. Let's look at this one here. This is one of the classic ones here. So, this chart basically says that Democratic women raise less money than Democratic men. If you take a look at this chart here, what seems to be the problem with this particular chart? What's wrong with this chart here in this instance? What do you guys think? What's misleading about this graph? Anybody tell me? The scaling seems a bit over-exaggerated. That's correct. But let's take a look here. Now, admittingly, based on what you see here, the title is technically correct. Democratic women raise less money than Democratic men. Sure, the difference here being 1.585 million and 1.4 million dollars. However, the difference between them is approximately $200,000 or 185,000 to be exact. And when you're talking millions of dollars, $185,000 is not a significant amount of money. And it makes it seem like a significant difference, especially when you start the scaling at 1.3 million. So, in reality, this is extremely misleading. It seems they're off by a little bit. They're not wrong in what they're saying, but the problem is that it's actually not as bad as they're making it out to be. Here's probably one of the worst ones here. Let me show this one off. All right, this one's pretty terrible. All right, let's talk about this one here. This talks about when former President Trump was being investigated and all that other shit. All right, so basically, this talks about Trump's tweets mentioning Mueller by name. Okay, well, let's take a look at this chart here. This chart is really stupid. This is like one of the worst charts I've ever seen. Like it ranks up there with Fox News' pie chart, which is just equally as bad. So what's wrong with this chart? A whole two times. That's right, Stella. Right? Look at the left here. So we're talking about one tweet, two tweets. A whole two tweets. Wow, this chart is very representative of a whole two tweets. It doesn't talk about them at all. And then suddenly, of course, it gets investigated. There's a whole two tweets about him. This is like a whole nothing burger. Okay, it's like who the heck cares? Exactly. There's a whole lot of nothing until the end. This doesn't matter at all. Look at this. This is garbage. This is a garbage chart. This chart is purely made to show people, oh my God, he cares. That's why he's mentioning him. Like this is the kind of narrative they want to push from the left. To talk about, at that time, President Trump and all that stuff. Like, okay, I get what you're trying to say, but you don't need this chart to really highlight that about two whole tweets. It's really stupid. Okay? It's really absolutely dumb. All right? Anybody can make two tweets in literally less than 30 seconds. All right? It really isn't that hard. I think everybody can agree with that. So this chart here is really ridiculous, and it's like, oh, you have 0, 1, 2, 3. If this was tens of tweets or thousands of tweets, okay, maybe that would be something I think everybody would agree. That'd be something pretty significant. But I think you can probably say two tweets doesn't mean a whole lot here in the context what we're working with. Yeah, so people say, hey, like I said, both sides of the aisle just as guilty. All right, just as guilty. It doesn't matter which side you're on. It doesn't matter. Like I said, this is not about politics. I want to say, hey, whatever you believe in is whatever you believe in. I don't care which way you believe in, and I don't care which way you lean. What I'm saying is that the tactics are work on both sides, and you can literally see it for yourself if you want. let me showcase one more thing here regarding misleading charts. Okay, now this one here is not really super politically leaning, but this is a government statistic that many of you are familiar with. Many times you read about in the news, we talk about unemployment. Okay, so if we talk about unemployment, this is a statistical website that's Shadow Stats. They take a look at what they feel real unemployment in the country is going to be. So this website feels this is their in blue. This is the website's estimation of current unemployment. The gray here is kind of like the broad estimate between them, between that and the red line, which is the government statistic that's pretty much mentioned in the news. Now, of course, there's a big spike here because of the fact that coronavirus happened last year. And of course, with coronavirus, a lot of people lost work. Okay, and we're sitting at home for like 2 months, and you couldn't really go anywhere and do anything. Hence the huge spike. And again, um, COVID started to die down. So again, with COVID starting to die down, that's a good thing. Hopefully, it continues on this path. I'm hoping so that this winter goes well for hopefully fewer people having fewer COVID cases. Hopefully, that'll start to die down. This Delta variant stuff goes away. But cross our fingers. But again, that's why you see it kind of start to decline a little bit. Now, the government statistic here that basically tells you that the unemployment is about close to 5%. That's what probably they'll tell you in an article or something that you'll read online. The shadow stats figures that the actual unemployment is close to 25%. So you have this broad range of a 20% gap between the official government statistic and this website statistic. Now, let's be honest with ourselves here. Is it going to be 25% unemployment? Is 1 in 4 unemployed? The answer to that question, in my opinion, is no. Okay, I think that honestly, it's probably somewhere between 5 and 25 as it states. If I were to be perfectly honest, in my opinion, it'd be like 15 to 20. That'd probably be appropriate, something more conservative somewhere in between. But nothing in the two extremes that you have here. Now, why is this important? Is because unemployment, and probably in a lot of ways, is one of the most misleading statistics actually shown in the media. Why do you say that? Well, one thing about statistics, as I mentioned here, it talks about how you came up with the number of 5%. Instead of saying it's 5%, you have to ask yourself, how do you come up with that number of 5%? What do you consider unemployed? And who? So basically, who do you consider unemployed? But more importantly, who do you not consider unemployed? You know who's not considered part of unemployment statistics? Homeless people are not considered part of unemployment statistics. How about housewives and house husbands? Nope, they're not considered part of unemployment statistics, even if they are eligible to work. Retired veterans who are eligible to work, certainly not part of unemployment statistics. People who just lost unemployment, um, and who are no longer collecting any money on unemployment, they are not included as part of government statistics. People who quit their job, not get unemployment, they also are not included as part of unemployment statistics. There's a lot of people who are not included as part of that 5%. And that's why the actual unemployment number is significantly higher than what's actually reported. So there's not a lot of transparency there because of how you calculate that unemployment number and who you include as part of that calculation. So I want to just kind of put that out there and be like, you know what? You kind of have to read between the lines and actually figure out how do you come up with that number there. When you look at a political poll or any other, kind of statistic there, ask how did you come up with that number? Is that number really real? Okay, and if you do a little digging, you can find out between the lines and you can say, okay, yeah, I can pretty much say that that's true, or you're in that right ballpark. You have that. We'll talk about it later. Talk about like say confidence or how confident you are about that particular statistic, or again, is it not? Tell me how you actually arrived at that result. Yeah, that again, things like that can certainly influence people if they're not aware about that fact. So something to keep in mind, most certainly. especially regarding misleading graphs. All right. Okay. Any questions about that? Any questions about misleading graphs? You guys are pretty chill with that? Yeah, unemployment's a pretty big one. So that's why you probably hear a lot of times, right? A lot of people, a lot of companies are looking for workers, right? Because they're getting their unemployment benefits, and then you know, the kind of, and then basically once they're no longer getting unemployment benefits after next month or this month or whenever that happens, then yeah, then they're no longer on the rolls for being part of the unemployment statistics. So, yep. All right. All right. Very good. Very good. Excelente. Excellent. 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 Okay. So, let's go to the big screen. Okay. So, this is where we're going to end off here for today. Next time, what we're going to do is we're going to do chapter 3. Okay, so that's what's next on the docket here. So the sections, if you're keeping track pace with the course here so far, these sections 2.1 to 2.3 are all of chapter 2. That is going to be, say, the homework assignments for you to work on if you're keeping pace with the lectures. All right, so that is what is on for you if that's what you're working for. Okay. Um, any other questions? Does anybody else have any other questions? All right. Very good. Very good. All right. I want to thank everybody for coming on. I had to stream here once again. Thank you so very much. All of you are absolutely fantastic people. You guys are what make this super fun and super enjoyable, super exciting. Thank you so much for bearing with me here today. We're going to get into a little bit more detail here for actual maths, for more math stuff here for next time in Chapter 3. Also, as a reminder here for Chapter 3, please bring your graphing calculator. We will be using that for that chapter. So, but we'll be going over slowly so we can get used to using that guy. So please bring your graphing calculator with you for next class on Tuesday. All right, and I will see you all then. All right. All of you have a very wonderful day. Have a very wonderful weekend. I hope everybody has fun hanging out with family at the pool, having a barbecue, eat some great food, have a nice time in this Labor Day weekend. All right, you all have an absolutely fantastic one. All right, and as always, everybody, stay safe, stay healthy, but most importantly, stay sane. Have a great one. Take care, everybody. We'll see you on Tuesday. All right. Happy Labor Day, everybody. Take care, everybody. Bye. Bye, everybody. We'll see you later.